So today we are presenting real-time process optimization for refrigeration systems, presented by Dr. Carlos Fernandez-Aballi. Carlos is concentrated on deploying applications for thermodynamic systems, and he has more than 15 years of experience designing and directing solar energy and sustainability solutions. Now, without further ado, we will turn the time over to Carlos. Carlos, the floor is all yours.
Good morning to our audience. I am very excited to be presenting the result of the work we've been doing here for years now, and which has culminated in seeing process improvements in refrigeration in the order of 5 to 10%. And I'm hoping to yield some information about that, how that has been done, and how can they apply to refrigeration systems. So in the next half an hour, I'll be introducing a little bit what SORBA is, which stands for Smart Operational Real-Time Big Data Analytics. How advanced process control works in the SORBA platform, the optimization of refrigeration processes, and more specifically, the Refrigeration APC that we've been putting together as a template. So why SORBA.ai? So SORBA has been a software solution. It has a web-based interface, and its goal is to make artificial intelligence and machine learning solutions simple and accessible to everybody. It leverages the experience of ITG for more than 20 years in industrial automation solutions, and cutting-edge AI solutions has been developed in robotics in-house, and it brings it together into a platform that is not only powerful from an analytics perspective, but also from a connectivity to industry perspective, and it's what makes SORBA easy. It's also aware that in industry control all the time without glitches is important. So whilst computational power is important to perform good analytics, therefore the platform has a seamless structure from the edge all the way to the cloud. This allows creating solutions that can adapt to every situation, and therefore have low barriers to entry, both technologically and economically. As we've been applying the solution across industry, we've developed out-of-the-box applications with range and have now been tested in many assets, ranging from power generation systems to the optimization of logistic chains in the retail space, to large refrigeration systems in the brewing industry. The key sort of signature applications, and which have different variants, are the advanced process control, the PDM, which is the predictive maintenance, digital twin applications, which allows for modeling and forecasting, vibrations analysis, and equipment effectiveness, which allows to determine how your equipment is available and how effective you are using it in your logistics or in your production process. All these applications together make a powerful suite for machine learning industrial applications. They come together in the SDE or smart data engine, okay, which allows them to create a smart APC. So what is a smart APC, or smart advanced process control? So most, some of you in the industry, in the audience, which are listening and do controls currently, say, well, but my controls are smart. I mean, they're full of adjusted set points. They react to the machines. They correct errors. The thing is, most control systems implemented in industry are actually based on rules. SORBA's advanced process control is based on data. And that makes a big difference into how we're finding the improvements in energy performance. So what the SDE does, you have your standard process, which is talking to your PLC, then goes to your OP server, your SCADA, or your historian. And you have rules and which are either processed here or directly on the PLCs, which write set points to your processes. What SORBA does, it puts an extra control layer over your existing control layer and takes in the process data into our real-time data acquisition application. And that brings it into a database that allows for visualization, for cloud integration as an option, and then sends the data set into the automatic machine learning trainer. There, when you've collected enough data, you can train your models, and this downloads a weight matrix, okay, into your data acquisition real-time engine, which then receives the process and predicts the set points in real time, brings them back to your server, and is constantly adjusting your set points, okay, for your control variables, so that your process is working in real time. So to implement an advanced process control, an APC solution, you have to pick an asset, you have to determine of your asset what you can actually control, and then you got to build a heuristic. So you got to see what is your optimization variable or your optimization metric, what is your objective function if you're going to maximize or minimize your optimization metrics or reach a particular target, your independent variable, which is then a system boundary. And then once you've done that, which is already quite difficult, and you want to do it with an AI solution, your nightmare starts. You got to determine your constraints. You got to program your tags and scripts. You got to collect your data, condition it, create your models, create your dashboards, verify your set point predictions, close the loop, validate your results. What's really neat and empowering about SORBA is that steps 4 to 11 are really easy to do. And that is a game changer. So very quickly, you can implement AI solutions that can be applied all over industry. And we have now many successful examples in the refrigeration space. We have boilers and heaters, kilns, filters, membranes, heat exchangers, compressors, turbines, in the transport systems, solving in real time the random walk problem. So there is a whole area of application which allows leveraging expertise that exists in each of these companies and empowering them with analytics and a powerful analytics tool that is simple to use, which can then bring a data-driven set point real-time optimization to your operational assets. So how about the refrigeration process? So how would we optimize a refrigerator? Well, let's just think about here why optimizing refrigeration is important. So there's about 3 billion refrigeration, air conditioning, and heat pump systems operating worldwide today, which use 17% of the global electricity. It means 4 billion tons of CO2 emissions per year. Okay, so if we were able to gain 10% in energy performance for refrigeration assets, we would be making a sizable contribution to the improvement of the climate change crisis. And what's most neatly important about SORBA is that you can do it with very, very attractive returns on investments and deploying it very, very quickly, meaning that it's a software solution which allows you to implement without having to modify your machines or by adding very simple sensor additions to your existing machines. So now let's think about what optimization is. So what is the goal of any optimization? Is to improve one or multiple aspects of a system's performance without deteriorating the compromises between the system components. So, I mean, this is what's happening in nature all the time with our natural worlds experiments. And what you see here is the optimization result of years of evolution of the bird bone. And here is the optimization result based on heat transfer, on a heat transfer solution for a heat exchanger. Okay, trying to minimize material use while maximize heat transfer. So optimization is happening everywhere, and it's actually quite a complex process. In industrial assets, you go through this general 8 steps to optimize anything. You gotta measure, you gotta identify what you want to improve, you gotta parameterize the process correctly, understand what you can control, what bounds your systems, what are the limits, so how far you can take your optimizations. Then you gotta build and create a search space, evaluate alternatives, implement solutions, create a baseline, and evaluate the improvement. This is a process that, for example, in mechanical design, sometimes can take years. In SORBA, we're doing a complex process like this in real time. So we're measuring our system in real time, and in real time taking decisions of how it should behave so that it does so in an optimal fashion according to a heuristic that you gave it. Okay, we do this through 4 general milestones, which include discovery. Milestone 2 is setting up the software. Milestone 3 is creating the advanced process control solution. Milestone 4 is evaluation and knowledge transfer. So what I want to talk to you about most importantly here is the creation of the performance metrics. Okay, so typical performance metrics in industry are either mass, energy, time, quality, pollution. I mean, it's the things that matter. And the general concept of a performance matrix is the result over the cost. In refrigeration, this is the coefficient of performance, and it's typically greater than 1. And it must not be confused with efficiency. Okay, efficiency talks about how well you can harness a maximum potential. And in the refrigeration system, that's an important understanding to have, because your system cannot perform as well any given day. It's bounded by the temperature difference it's operating at and the maximum possible efficiency that you can attain across that temperature difference. Okay, so many of you probably have heard of Carnot and Carnot refrigeration. So a refrigerator is the inverse of an engine. And then you put a heat sink and a heat source, and you can extract work. In a refrigerator, you gotta pay for it. You gotta give work to then move heat from a colder space to a hotter space. In this case, the hotter space is your ambience. Okay, so your maximum performance is necessarily capped between the temperature difference of your loads and your ambience. And this parameter is a maximum temperature difference across the plant, is what bounds the optimal performance of your refrigeration system. It's also what you're trying to do, is what you're paying for. Okay, so how does that work in an actual refrigeration cycle? Well, you have your cycle, your gas, which goes around your refrigerant, in this case is ammonia, which goes around your cycle, follows this process where it's evaporating at a low temperature, compressing in a cooled compression, then condensing in your condenser by yielding heat, okay, and then expanding through your throttling valve back to your cold space where it can take heat from your loads. Okay, so you can work with two metrics of optimization. One is the COPC, which is, we call it the cyclic coefficient of performance, which can either be the isentropic, so meaning no heat transfer during the compression, okay, or adiabatic, or it could also be the polytropic, and we have implemented calculations out of the box to be able to do that. Ideally, if the plant is correctly instrumented, or even better instrumented, we have temperature and pressure here, temperature and pressure here, and we have a good characterization of the loads. And in that case, and we can measure electrical consumption during the compression. In that case, we can get a true COP of the system and use that as the optimization metric. Okay, so, and this is how a typical heuristic works. So in this case, we are using the COP, and the blue line is the mean performance of a system. This is data, real time, the system. We remember our bound was the temperature difference between the coldest load and the ambient. So that's what you're paying for. And as you can see, at 16 degrees, okay, you have your temperature, your system can perform with a high coefficient of performance over here, or with a low coefficient of performance. And that spread happens throughout different temperature differences. What the APC is doing is saying, okay, so what's my average performance? And saying anything above average is good behavior. And is setting the control set points, so what is controllable, the control variables in your system to operate like in the green line. And in this case, we're seeing an improvement, say, around here from 6 to 8. So that's almost a 30% improvement in performance in this particular case. So how do we do this? How do we put a refrigeration APC together? Well, the first thing is we got to understand your system. So your system needs to be, the way the solution works is you divide your system in lines, which are groups of compressors which tend to a particular cold temperature or low pressure recirculator. Okay, and then you got to program the different parameters of your loads and of your compressors and of your condensers, okay, and bring it into the SDC. So that will be your first step. So you create your data settings. So you create a data structure, each line, and all the different parameters within each line. And then you got to calculate your COP, your COPC, your enthalpies across the system in order to linearize the performance of your system. So to help the artificial intelligence use the metric of optimization, the heuristic that we had seen before, and find that optimal behavior. Okay, so once you program your data settings, so you know what you want, but you can connect each variable directly to your PLC or to the OPC UA server. Through Modbus TCP, there's over 20 different industrial drivers already set up in the SDC to be programmed through your channels. And you got a group of dashboards that are already created, which are easily programmable to be able to see all your process variables in real time. So once you've confirmed that all your measurements are adequate, you can go ahead and configure all your scripts. And in SORBA, these are already, in the refrigerations application, these are already made for you and just require simple modification. And the way the scripts works, it looks at the cycle parameters. So all the enthalpies and all the pressures across the cycle. It then does a power calculation to determine the instantaneous efficiency, and then does an energy calculation to be able to build a baseline for a determined performance, not in every instance, but over a period of interest. Okay. Once all of these things are configured, again, you got dashboards already created to be able to look at your COP, your ideal performance, your energy metering. And once you can make sure that everything is working correctly, you can start data collection. The data collection period can take anywhere between 2 weeks to a month, depending on how your refrigeration assets operate. So if you have a refrigerator that operates for a short burst of time and then is off for a long time, and then again, that will require more data because your actual operational time is much less than the period that you're waiting for data collection. And with that, you can decide how you want to control your system. So in some systems, you'll be able to control your discharge pressure, your suction pressure, and the speed of the fans in the cooling tower. In other systems, it'll be just your pressure, your suction pressure, and discharge pressure. In other systems, it'll just be fan speeds and pump speeds. I mean, it depends what you can control in each system. And then there are more adequate optimization independent variables and metrics for each of these control strategies. And of course, they have different saving potentials. Okay, so you build your data set. And once you have a data set built, this is now in the machine learning trainer. Okay, you can upload hot data, which you can upload a CSV file, you can create a project. And the projects are created by models. So you create an analysis and choose the type of analysis you want to create. And this allows you to get back to the regression line. In this case, now we're looking at the isentropic COP as the optimization variable. And as you can see here, this is exactly the same system, in fact, that I showed you before, but you only have a 10% improvement in your cyclic COP. And the reason is that this is not taking into account the electromechanical efficiencies of your compression system. It's happening in the gas side of the compressor. So your opportunity for optimization is more humble. Okay, with your heuristic created, you can create a model, and you can retrain your model as your system changes seasons or your boundary conditions change. Okay, and this model, for example, has been retrained 3 times. And here, you just hit the deploy, and it goes to your machine learning, to your real-time engine, and there you map your tags, and you can see the results. So here we have now, this is a screenshot from a real result, and this plant has a fixed set point of 1.8 bars. And here we're controlling the suction pressure of the plant, and the blue line is where your process variable is, and the purple and yellow line is where your COP or your cyclic COP, your isentropic COP process variable would be seen. As you can see, they're both concurrent, so they're both achieving the same kind of optimization. And in both cases, during all this time period, which is about 6 hours, we would be saving energy, relaxing the process variable from this blue line up to where the purple line or the yellow line is. Okay, then you have an optimization dashboard that is already created, which allows you to see your savings in real time, both in percentages, in energy, in cash, and in emissions, and understand how the process works. Okay, here's another heuristic. This one now is looking at the effectiveness of the cooling tower versus the general COP of the plant. And this was implemented in Agudos in Brazil. And in this case, in a 15-day period, we saw $2,500 in savings, which would add up, could be extrapolated to $36,000 of savings in the year. And this application, after implemented, had a payback of around a year. So we were very happy with this result. So that said, we can conclude that SORBA is an easy-to-use horizontal industrial ML platform, that APC optimizations in refrigeration assets can yield between 5 to 10% increase in COP, sometimes more. There are significant economic and environmental gains for implementing a refrigeration APC. That templated solutions, like you saw the one in Agudos, can accelerate the deployments and improve ROIs significantly. At this point, thank you very much for listening, and I look forward to your questions.
Awesome. Thank you, Carlos. All right, so we will go ahead and take this time for questions. If you have not had a chance, please make sure you use the control panel to write them in there. It does look like we have one question. Did you take the consideration prediction maintenance, like check health of machines, temperatures, RPM, etc.? It could be a compressor or water pump process.
So in this advanced process control solution, we're not taking into account the health of the actual assets. So, but that is not complicated to do in SORBA. Once you've programmed your solution, improving the performance of a pump, cleaning a heat exchanger, adding another line to your system, it's as simple as programming, bringing in the new tags, programming the new assets, waiting for some data collection, and retraining your model. Once you've retrained your model, this will incorporate the new behavior, and your optimization will still be effective. By the way, these dashboards that you saw, these heuristics that you saw, are actually of some of the best performing systems within one of our clients, which has refrigeration assets across the world. And we were actually surprised. I mean, we were not expecting to find that much capacity for savings in the refrigeration assets of well-maintained, highly optimized refrigerators like these. So there is real value in looking at the data in real time and setting your set points in real time. Did that answer the question?
Awesome, perfect. It looks like that was it for questions. I do see, a few people. Again, I apologize if you had any technical issues, couldn't hear us or couldn't see the slides. This webinar is being recorded and it will be sent out to everybody at the end of the webinar. So rest assured there. Also, if you do have any specific questions that come up, maybe after you watch this recording, you can email me directly at sbeverage@sorba.ai. I'm going to put it into the comment section to make it available. Actually, one other question just came in. Is it same algorithm or methods for APC optimization in different applications, like for healthcare, hospitality, or any APC?
Okay, so if we were going to, so for the refrigeration asset of a hospital or of another processing facility, we would have the same refrigeration application. Okay, as long as it's a compression refrigeration cycle. If we had another type of refrigeration cycle, which they do exist, we would have to revise the script to incorporate the new behavior in the compressor. That said, it would be the same general process. For example, in the case of a CO2 cycle, which is quite common now, becoming more popular, these scripts would work almost to the point, especially if you can measure at the COP level. Okay, so while we would have to revise the cyclic behaviors, okay, the power behaviors, if we had the measurements of the loads and the electrical power provided to the system, we could go ahead and very quickly implement the solution with this same scripts and templates.
Awesome.
That answered that.
Does anybody else have any other questions? We still have some time, so we've allocated about an hour for this. If anybody else comes up with anything, we'll give it a couple more minutes. Carlos, is there anything else that maybe you want to cover? Sure.
Often people are shy with questions at the end, etc. So in order to prime a conversation, I went ahead and I have a system running here, which is operating halfway across the world. And I thought I'd show you a little bit of what the web config tool looks like and what the SEC looks like. Okay, so I'm just gonna go ahead and share my screen again and run you a little bit through that. Okay, can you guys see my screen?
Yes, I could see it.
Okay.
Can everybody else see it as well? Give us a thumbs up. Maybe a comment in the comment section. Okay. All right. We got one thumbs up. All right. We're good.
So here's the here's the web configuration tool for the SDC, and it starts with an overview of the system where you can see how your system is performing, and then a device setting tags that allows you to quickly, very, very quickly, in a almost a wizard way, connect your system to the network where it's going to operate. It also allows to configure an OPC server in your system if you want to broadcast data out elsewhere. Then you have your data settings, and this is key. Here, you map your channels and your assets, and you can have N assets, not only refrigeration. So one is according to whatever licensing agreement you have, can let you do multiple assets at the same time. And by the way, the SDE can run in any computing device, basically, that can run Ubuntu. So it's a software solution, not an actual physical gadget. It can run on a virtual machine as well. It can run on a server. All right. Then say your lines here. You can program all your process variables, which in this case we've set up as your as PV variables. So this system has 11 compressors. Okay. All the ranks that you see are actually from a predictive maintenance application that is also programmed in this system. And as you can see, it can be quite complex, given all the different process variables, and you don't know which ones are going to be important. For example, here is the tag ranking. That's very small. Maybe you guys can see it better there. Here's a tag ranking of another refrigerator, and this is, for example, line 1, and it's saying that the inlet pressure of the cooling tower is the most important variable for the optimization in line 1. You say, well, that's trivial, right? Well, it's true of line 2, but it's no longer true of line 3. The heat transfer is more important in line 3 than the inlet pressure of the cooling tower. And in line 4 is actually the enthalpy inlet into the throttle. And that's because line 4 has is the cascade line. The system is in cascade, meaning it is line 4 who feeds the refrigerant into line 2, 3. So basically what this is saying is that the condensation temperature or the condensation energy is one of the key optimization variables, okay, which is also coherent with the enthalpy out of the compressor, okay? So, but as you can see, as you come down, you start to get non-trivial results where, for example, even though line 1 to 3 cascade from line 4, the parameters of line 1 and 2 and 3 can determine the performance of line 4, and that's because they're all connected through the condenser. And it's very difficult, and they're not consistent. Therefore, it's very difficult to understand, how this system interrelates unless you have a tool like SORBA to be able to do it. Okay. Also, the zeros here is where the tags stop being important. So over here, the heat transfer, the cooling tower, is of no importance to the optimization of line 1. At the same time, it's very important from line 2. So you say, well, we have an excessive number of tags. Well, sorry, for line 3, which is right here. Okay, so you say, okay, well, this it's the same in all the lines. I'm sorry, but this is the same parameter for line 3, and you say, well, why do we need to optimize with all these tags? Is because when the system behavior changes, you do not know if other tags are going to gain importance with relation to others. Okay, this was trained in the winter. Maybe when it happens in the summer, we're going to have a different behavior. Let me show you more of the system operating here. So here's your machine learning trainer. You can create this where you create data sets. Okay, and if we create one version here of your data set, for example, just show you how simple it is. It's not gonna work. Fun. Okay, yeah, I don't know, my keyboard decided to act out. Let me see if I bring it closer here. Yes, it's acting out. Okay, I cannot show you that because of my keyboard. Here's another optimization heuristic of a different refrigerator. Okay, this time showing a more modest efficiency gain. And here's again our open loop. And this jumping that you're seeing is created by the maximum high limit, minimum low limit. And that is an important concept, because you say, well, how do you keep control? How do you know if we don't have a wacko prediction that is not going to give a wacko set point and break my system? And the answer is that the optimizer will only give a set point within a optimal high limit or low limit, which is determined during the training process. So if we go to the general parameters here, okay, it actually determines your optimal low limit, your optimal set point, and your optimal high limit. And your prediction, your real-time control, is happening between these two limits. If your process variable or your prediction exceeds these two limits, the system can either enters into a ramp or jumps your set point directly to the mean. So it slowly brings your set point down, or brings it to the mean and brings it to the bottom of your low limit, trying to bring the system back to behaving within the optimal bounds. And that's what you can see here in these jumps in set points, okay, is when the prediction is departed from the high limit. There's an open loop optimization, so it's an open loop graph. So your blue line is your process variable, your green line, your yellow line, sorry, is your cyclic COP set point, and your purple line is your actual COP set point. And as you can see, sometimes you can gain improvements and sometimes you can't. Sometimes you cannot rise. And the system is saying, actually, to behave optimally, you have to come down to find the red line, the purple line, and spend more energy. So what I'm hoping to show you, or to make apparent, is that these are not non-trivial problems, and it's very difficult to make good decisions. I'm going to see if I can show you that. Oh, it doesn't write. I can show you the PDM application operating, because it's been disconnected. And this is a real life system, so I have no control. The operators are connecting and disconnecting things. Okay, so the PDM application is not working, but basically over here, we've done an application per heat exchanger, where we have a tag ranking. See if I can show you it'll show in the last 30 days. Hopefully we'll have some ranking show up. So it basically ranks your tags according to what's happening, and it tells you which tags are contributing to an anomaly being created. And over here, you can track when the anomaly is happening, and it will flag an error when the anomaly is long enough. When the anomaly is happened for long enough, that we need to be worried and check the heat exchangers. And when this came up, we were able to flag a falling heat exchanger about 3 days before it happened, and the plant had to shut down the heat exchanger later because it was actually fouling, and confirm the anomaly detection. Okay. So yeah, that's more or less the SORBA team. I am hoping in this sort of laissez-faire look, I mean, to create the analysis. I'm just going to pick any here. Okay, it's very simple. You go ahead. Anyhow, you select your tags, and then you go through the process, build your filters, and then you can say, well, I want to cluster, classify, regression, optimize. You select your optimization. You select your optimization variable, say line 1 COP. For example, you're going to maximize it. Okay, you select against what, where, against my temperature difference across the plant. And what are we going to control? Say we're going to control the suction pressure. Okay, and then you move forward and you say how many of the data set versions that you want. So here's got 3 versions, and you train. And I'm not going to hit the train button because it'll take a few minutes to do it, and I want to answer the questions. But this would create the same models that are already here. So we selected the COP. So this would be the result of that training. Go ahead, Steph. What questions do we have?
As you were speaking, somebody mentioned how many plants have this system installed. I think it was initially while you were explaining the regression lines.
Yes. So this is installed in more than 30 plants at the moment in one of our clients, and we have over 100 different case studies across the world in different APC applications. But this specifically one is now installed in more than 30 plants across the world. So South America, Central America, North America, Europe, Africa, and Asia.
Awesome. We got 2 more questions. Do you have resources, documents on which we could get all algorithms or formulas used? Any handbooks?
Right. So I mean, as much as I like open source solutions, and we work with open source solutions all the time, the application platform is actually so SORBA is a proprietary application, and of course there's documentation available, and you can go to SORBA.ai website to see it, or contact Steph or myself for more details. Okay. Then on the refrigeration application specifically, I mean, a lot of it is just classic. It's application of classical thermodynamic theory to an AI context, and you can't really perform so I would reference you to any actual textbook. So any thermodynamic textbook will have the explanations of the indicators, what the COP is, what the isentropic COP is, what the polytropic COP is, the relationships between the different efficiencies. Okay, and what we have done is basically taken established engineering and empowered through a data-driven approach, which is what SORBA allows us to do. The actual scripts, well, if you implemented a SORBA application, we could and bought an APC, we would have the scripts available for you. Okay, if you wanted help with something, reach out. We're not reselling anybody's solution. It's our solution. Okay, so anything we can do to help somebody, we most likely will. Okay, as long as it makes sense.
Awesome. Last question. What machine learning models does SORBA IoT use? For example, clustering.
Right. So clustering models are used, for example, in predictive maintenance applications, and where you try to understand a particular behavior. Yes, where you try to create understand where particular behaviors belong to, which would be a classification model, where you say, okay, but how do you know what is a class? You got to create a cluster about that class. Okay, so it allows you to identify how data clusters and what new data points belong to what clusters. And we do that in predictive maintenance applications all the time to be able to detect anomalies.